So one of the Piazza questions was 18.9C, and it has this alpha beta unsaturated ketone that is attached, has this methoxy group on it, and somewhere it gets converted to an aldehyde. I'm going to mute everyone on entry just so that we don't have any extraneous noise. All right. So this one is a little bit different. It actually gets back to the idea of the reactivity of enols. So we have an enol ether here, and this is kind of a confused pi system because we have electron donation from this oxygen, and then we have this electron withdrawing carbonyl next to it. So in order to protonate this molecule, there's actually two places you can protonate it, and one of the two ends up going towards, actually you could probably protonate it either one. It's a little clearer to see if you protonate at the double bond. Either of these reactions, we could either have the carbonyl oxygen attack and take a proton, but since this double bond is electron rich on the alpha carbon, you can also draw out a mechanism in which the lone pair on this oxygen comes down and gets protonated. This leads to a faster solution, so I will go down this pathway and show how that works. So since that's an electron-rich double bond, we can protonate it, and we end up getting to this oxocarbenium intermediate. With a ketone on the other side. Since we have aqueous acid around, and under acidic conditions, we now have an activated electrophile where the water can now go in and attack. This will go to our tetrahedral intermediate. We do the usual proton transfer because we want to make the methoxy leave. Eventually we need to get back to this aldehyde. And this is going to follow a similar mechanism that we've seen for acetal hydrolysis. So we make the methoxy group into a good leaving group as methanol. This leads to a protonated aldehyde afterwards. And neutral water will take it away. So you don't want to use hydroxide. There's not going to be any appreciable concentration of hydroxide in solution. And that gets us to the product. Do we use the ester because it's more nucleophilic than the ketone? Either one would work. I can show you why. I can draw the other equilibrium over here, what that looks like. Because if you protonate this oxygen, I think this is what you mean. We can draw a resonance structure where actually these electrons can be pushed down, over, and up. And then the hydrolysis mechanism will end up looking quite similar. Only now you're going to have an extra tautomerization event afterwards. So you could also have water attack this species and keep on going, and you would get to the right answer. But since we see the hydrogens appear, a new hydrogen appears between this double bond, it could either come from tautomerization of this enol, or it could come from just direct protonation. think this is all I need to say. So there's a question, why don't we want to use hydroxide? We don't want to use hydroxide because we are under acidic conditions. So in neutral water, there's, tiny amounts of proton and hydroxide around. If we go to an acidic solution, then essentially that goes to completely zero. And that's where I start to take off points. So if we're under acidic conditions, we want to have all protonated intermediates with neutral nucleophiles attacking. Boom. Ooh, I like this question. This is 1819D. And somewhere along the way, we have a fragmentation reaction. Again, we want to notice that these reaction conditions are acidic. So we're going to use a different mechanism to attack the carbonyl than we would under a basic solution. And along the way, we can see that we are somehow going to break open this bond. So it could attack either of the ketones. And this 1,3-dicarbonyl is a little bit special in that the hydrogens in between are less acidic than normal because it's difficult for this enolate to become planar. It ends up, or even the enol form, because if you try to make this sp2 hybridized, it has trouble becoming flat due to ring strain. But for this reaction, we're going to start with protonated methanol, because if you add sulfuric acid to methanol, you will make protonated methanol. The plus. We know that we're eventually going to be adding methanol to this carbonyl. This can be a hint as to where to start. And it's this four-membered ring that actually drives this forward because they are strained and this promotes the ring opening. Since we're under acidic conditions again, we want to have all neutral nucleophiles with nicely activated or protonated carbonyl compounds. We'll have methanol come in. It will attack. And now we're going to do a proton transfer, and it may not be completely obvious at first. So the thing we're trying to kick out actually is not this hydroxyl. What we need to have as a leaving group is this carbon. We're trying to kick out the electrons and go that way. So what we need to do is actually have a proton transfer that activates this whole pi system as a leaving group. We're going to draw a proton transfer. And in order to make this a good leaving group that isn't going to be negatively charged, we are going to have to protonate the carbonyl. So this is a pretty tricky problem, as it involves some steps like retro Aldol or retro Claisen. Intramolecularly, this would be a retro Diekmann. I think we never used that name. Organic chemists have names for everything. But this allows us to be consistent with having a leaving group that is already activated. It's just now a bit more remote. This generates the leaving group in the enol form. And we see we have this methyl ester afterwards, only now it's protonated. And to do the tautomerization, we can invoke a proton transfer, where we're going to transfer this hydrogen to this carbon now to get us back to the keto form. We kind of do both those steps at once. And then methanol will take this proton back. Yeah, the reason we didn't talk about this, and I won't test over this, this is a concept that I would have mentioned a bit more if we had more time, the geometric effects on enolate resonance, but I'll mention it briefly. So in order for us to have resonance in something like a 1,3-dicarbonyl, if we have, base around, this will get deprotonated. In order for all these carbonyls and lone pairs to communicate with one another, we need all of the pi system to be aligned, right? They need to be flat. So they can be bent, but they all need to be in a similar plane because it's the p orbital overlap that helps this out. If we try to make an enol form of this molecule, it actually becomes very difficult. So whether you draw it this way or you were to try to draw it this way, because of the geometry, it makes the hydrogen bonding a little bit more difficult just due to distance. Maybe I'll draw this more in the middle. It's a longer way to go because the bonds kind of force it to be out. You could have used either one. Okay, let me finish this thought. And so this is kind of why it's not very basic. And the same thing would go if this were an enolate as well. So we can imagine this being an enolate and just changing the geometry of this center ends up making it very strained on the overall system. Again, this is not something that I'm going to be asking about on the test. But if you thought, why doesn't this exist more in the enol form, that is why. All right, needs to be flat. Doesn't want to be flat. So there's a question on why I use the lone pairs of the OH versus the methoxy. You could have done either one. I'll use a different color arrow and draw that. So if we used these arrows, this could have come down and done the exact same step. And we'll see if we did that. I'll switch back to blue. It's a little better contrast. We'll end up with the OMe positively charged in the OH. This will still be in the enol form. And these two are resonance isomers of each other. So if you take these electrons and just push them down, you get the same thing. So really they are the same molecule all around. From this picture, I think the deprotonation's a little bit easier to see. In this molecule, you would just push the electrons around whenever methanol came for this proton. So then you would draw it. Oh. You would draw the electron bond. This would come down and through. Yeah. So, and this is generally true for collapse of any type of tetrahedral intermediate if you have the OMe and the OH, and you could choose either one. In the end, they make the same structure. All right, and this is another one that people wanted reviewed. So this is our basic Aldol reaction, but I'll draw out the steps again. So the things we want to note is that we are at reduced temperature. So we have 5 degrees C, That means that we'll be able to control the E1CB elimination. We have sodium hydroxide and water. We don't have anything that can hydrolyze, but we do have this alpha proton here that can be deprotonated by hydroxide in equilibrium. There's going to be an equilibrium. We're going to go to the enolate. If it helps to follow these reactions by drawing the carbanion, go for it. And these will be nucleophilic at carbon, and that's why this is useful. So this is a dimerization reaction, so we can see how in the molecule we actually have two of the starting materials. So we have a negatively charged good nucleophile. This can react to carbon to attack 1, 2 onto the aldehyde. So I'm drawing this in a slightly different arrangement from as it's drawn in the answer, but it has the same connectivity. And then finally, we just need to protonate and we get our aldol product. All right, I think that is the last of the Piazza questions, so I can go over to extra synthesis practice problem 2. And I can go over the last sodium hydroxide step on the practice exam. Since I see this right now, I'm just going to pull this over, but I'll do the other one first. Ooh, there's all sorts of stuff here. So you mentioned just the last sodium hydroxide step. I think you mean this one. I'm just going to copy and paste this whole thing. Copy. Paste that here for now. I need to go find extra synthesis practice. Where do I have it? Ah, topic 7. So this is number 2. So I will copy this over and then we can talk about it again. The ring formation step. Okay, so we're looking at this step here. We had to make one of the esters into an enolate. I was wondering how we would make sure only one ester becomes an enolate. So in the solution, there's a couple, I think the important thing is I'm not going to draw it out, the whole thing. Let's just say this is abbreviated. If we think about sodium methoxide and where the equilibrium lies with enolates, we only make very, very small concentrations of the enolate at a time. As soon as we make it, it's quite reactive. And so then it'll be able to react. But all of these are reversible steps. So if we have, we can compare this by thinking, what is the pKa of an ester? This is around 25. The balance on this would be then plus methanol. And methanol's pKa is 16. So really these are methoxide's like just barely acidic enough to be able to deprotonate an ester and make these reactions happen. So we can be fairly confident that only one side of the ester will be deprotonated at a time. And even if both happen to deprotonate at the same time, there's always an equilibrium that'll get us to the situation we need. So this is not like LDA. If you used LDA, then we would be using our essentially single-headed arrow here. And you would make exclusively this type of enolate. Electrostatics will also disfavor the double ionization of that single molecule a bit. Last sodium hydroxide step. How does the reaction work? I believe you mean this reaction? Oh, cool. Yeah, okay. So the first step is going to be just hydrolysis of the esters. I'll blow this up a little bit. So initially we get to this doubly deprotonated state. Then we add acid to make them neutral carboxylic acids. And you have to draw one of the carboxylic acids kind of rotated from the other one to be able to write this next mechanism, right? And when you heat up these types of carboxylic acids, there is a loss of carbon dioxide that can happen all at once where these bonds go in a circle. The proton that's already hydrogen bonded to this hydrogen in the middle can kind of take it all the way, and we lose CO2 all at once. This leaves us with this weird enol form of the carboxylic acid briefly. That very quickly in solution will tautomerize back to this carboxylic acid. There's another question. Why could we not use methanol to turn the product back into let's practice, no wait, problem 10. Here we go. Practice exam. That is this one. Could we change the last two steps to sodium hydride and then sodium hydroxide methanol? So you wouldn't want to use sodium hydroxide and methyl iodide to do the last step, because if you try to deprotonate the ester with sodium hydroxide, we're going to get attack on the ester, and this would give you hydrolysis. So you would end up actually going backwards after workup to the carboxylic acid. So we really want to put the ester in first, then we can use a very strong base like LDA to deprotonate this alpha hydrogen. So in this case, that order would be important, and probably the choice of reagents as well. Something you could probably get away with. Oh yeah, you could totally use sodium hydride here. Where do I have sodium hydride? Here, you could use sodium hydride if you want to. You could use sodium hydride here if you want to. Sodium hydride's a great base. Use sodium hydride there. You could also, as I mentioned, you could have turned the alkyl bromide into an alcohol and then use that as like a DCC DMAP coupling. The other base that you could probably get away with here would be something like this, where you're matching the alkoxide base to the ester, but that still wouldn't be as good because you're going to have competitive attack and Williamson ether synthesis with the desired alpha alkylation. Sodium hydride is not the best at deprotonating esters. It actually takes a long time. It's more from a practicality standpoint. In principle, it should be fine. I would say on this exam, if you need to make an enolate, there's very few times that I would not be going to old friend LDA, unless it's the more hindered site. LDA will cleanly solve a lot of your problems. If you need to do a crossed Aldol, don't, and it solves a lot of the problems. And just make sure to draw the enolate formation first, then add in whatever electrophile you want. It's just 3 letters. Makes life nice sometimes. Cool. For problem 11 on the practice test, we not use methanol to turn the product back into a ketone. Let's go take a look at 11. Oh, so you're asking, oops. You're asking why not do this? This comes down to pKa's. Methanol's pKa is about 15. This molecule's pKa is, let's say 10. Actually, it's probably close to 11, 10 or 11, around there. And so 4 orders of magnitude is still enough to really be almost entirely in the deprotonated form. 4 pKa units gives you a lot. So really what you have in solution at the end would be this. There'd be tiny amounts of this, of this around, but it would be certainly minor. We're going to practice exam 12. Ooh. 12A. Okay. So this is one of the deuteration questions. So we're looking for what types of hydrogens can be exchanged with deuteriums. And so to answer 12, we need to look at which hydrogens on the molecule are fairly acidic. And the hydrogens next to the ketone will be the most acidic. The methyls over here won't have any resonance stabilization, so these are going to be super high pKa, 50 or 60. But these hydrogens over here will be around 19. I'll make them green. And so these are sufficiently acidic for hydroxide to make an equilibrium. It's still going to favor the ketone in solution based off of pKa's. But we will be able to make this enolate and now we're running the reaction. Oh, I apologize. This should be a deuterium. We assume deuterium oxide will have the same sort of basicity as normal hydroxide. But now we put this into a D2O solvent. So we're going to have, a bajillion molecules excess of deuterium. So as this equilibrium occurs, we will start to get exchange of these 2 molecules, deuterium. And there's still going to be 2 hydrogens on here. And over time, these will continue to exchange with deuterium and D2O to then give you a second deuterium. And this will keep going until they are all exchanged. So the goal here is to identify which protons are exchangeable and essentially switch them to deuteriums. There was one that was a bit trickier in the lecture notes where we did the same reaction with this cyclohexenone, and this ended up getting deuterated in a number of places, including this position here that doesn't go through a direct deprotonation, but rather from the al anion from deprotonating one of the hydrogens right here. You can go, I think we wrote that out pretty explicitly in the practice, but that should be maybe useful. 12a, can you add a carboxylic acid as an R group in malonic ester synthesis? So I'll draw this out. So this becomes in the problem here. So if I understand what you're asking, you want to start with like malonic acid instead of starting with an ester? Or are you saying you want to instead somehow go and have these as R groups and you want to turn it, or sorry, say these are just methyls, so I can use my R group somewhere else. And you want to make this. Is this what you mean by R? Yeah. There isn't a super good way to do that, actually. The best way would be using some chemistry that you guys don't know. You would not be able to make this enolate and add in CO2. So that would seemingly be the easiest thing to do, but it is actually not favorable. It would actually, and this is part of the problem, is it's too easy to lose CO2 and go back to the initial malonate. No problem. 12C, 12D on the practice exam. Absolutely. Okay. So this is an enamine alkylation. So this is from lecture 30. I'm looking at, yeah. And so enamines are nucleophilic at carbon just like enolates. They react with very good electrophiles like allyl bromide. So we're going to push the electrons from the nitrogen down. And this is a reaction that a normal enol with an oxygen would not be able to do. So this is something that is special because of the nitrogen. The nitrogen makes it more nucleophilic because nitrogens have more electron density. Sorry, I was checking something. And this is what we will make initially. We would make this aminium, the bromide counterion, and then water will come in, attack this, and then proton transfers, loss of the amine, give you the product. We'll just say proton transfer, elimination, and minus a proton. You'll have to deprotonate it. For 12D, this is going to be similar to the haloform reaction, only we don't have a methyl next to the ketone. We have an ethyl. And turns out you really need to have all 3 bromines on that carbon to make it into a good leaving group. So in this case, we're going to have sodium hydroxide. I'll make this a little bigger. Once again, this is going to act as a base. It'll make our enolate. Could be a minor contributor, but we make enough in solution to do this reaction because this will quickly react with bromine. We need a bromine around. This can come down. This can attack. We make 1 alpha bromide, and then there's still 1 more hydrogen that sodium hydroxide will take, and we'll go through the exact same process again. I'll just draw 2 little arrows, and that gets us to the dibromide. And so this won't be eventually hydrolyzed to the carboxylic acid. We're going to stop at the dibromide. 2 is not enough to make it a good leaving group. What do you mean by other circulation pathways in number 11? What was I saying? Oh, maybe I meant other cyclization? So this would be the other cyclization possibility, where this ester enolate will attack this oxygen. Oh, I misdrew this. I apologize. I'll try to correct this. This should just be like this. That shouldn't be a ketone because we don't have anything to kick out. Yeah. Because this can be protonated, but it'll always be going backwards. It is still true that the issue is the lack of, I guess actually there's twofold, right? There's a lack of a leaving group, and there's no alpha proton here if that were to leave. So actually this has a lot of things going against it. The ester has a good leaving group, which lets it get to this deprotonated pathway. This one never can eliminate to get to a sort of downhill spot. And it doesn't even have a leaving group next to the alcohol. I will go and update this. I'm going to erase some of these comments just so that when I re-upload, people aren't confused by my extra writing if they can't hear me talk. Yeah, this looks okay. So I drew 2 arrows. I will go and make this an alcohol. Okay. Clarification on 6. Oh, formaldehyde in this reaction. So formaldehyde actually becomes one of the carbons. So we see, let's track formaldehyde through the places. So this is formaldehyde here. This is where the formaldehyde goes. And this is where the formaldehyde ends up in the product. Yeah, this is the Mannich reaction. So the aldehyde and the secondary amine, these will be in equilibrium with one another. To form this with a little acid catalyst. So this is one of those sneaky ones. Mannich reactions take place between an aminium. An aminium is almost always formed between the amine and the aldehyde, because this reaction is really fast. Formaldehyde is really reactive because it's not sterically hindered and it's electrophilic. So it can make a good amount, of this around. And also under the acidic conditions, we can make the enol form. So we have our enol that's attacking a very good electrophile under the somewhat acidic reaction conditions. Why is 9 on practice exam B instead of C? Oh, okay. So this is, I think the way to look at this is where is the nucleophile and where is the electrophile? So if you look at where the enolate is, so the enolate that forms, because I just drew a sort of conceptual representation. So the aldehyde has nothing on it that can deprotonate. It's non-enolizable. And so that means whenever this becomes attacked, it's the side with the methyl group that ends up going to the alcohol. So we want to track methyl going to the alcohol. Notice that on C, the methyl is on the ketone form. So that would not be the right one. Does that make sense? Cool. Yeah. Making sure you have the partners right. And so A is ridiculous. And you know that because we're at no elimination, we get rid of C and E, or D and E as well. Yeah, I don't know how you could get, oh, yeah, A. There's some catalysts that can make things like A, but that's for you want to go learn organic chemistry in graduate school or something. Maybe you do. You guys got any other questions? Or things I can help out with? Follow up on 9. Yes. So things that will be consistent, and I will follow up on. Okay, you have a follow up on 9. The aldehyde is not enolizable. And then I'll mention the manic reaction again. So in order for us to make an enolate, we need to have protons alpha. And so there are no alpha protons. So we won't be able to deprotonate it, which means we can't make the enolate and it can't react the other direction. So this is one of our cases where we can have a selective crossed aldol because one is non-enolizable, the other one is. Going up to the manic reaction, things that will be consistent in the manic reaction is you will have a secondary amine, you will see formaldehyde, and you'll see a ketone or aldehyde. So it's always those three things. I think the combination of the secondary amine and formaldehyde will be the kind of giveaway to start thinking that it's the manic reaction. And you just need to imagine the aldehyde or ketone then attacking the aminium. So it's sneaky because it adds in that one extra little carbon in there. And these reactions work better than you would imagine. You think that having all these different pathways and things going on, it wouldn't be very good, but it does. And there's also other ways. Would an aldehyde with 2 carbons add 2 carbons? Yeah, but you don't see it as much because it's a little slower to make the aminium. And especially for this class, I'll keep it as just a 1 carbon unit. Hypothetically, if you had something like acetaldehyde, to methyl here. But these end up actually not having very good yields. Formaldehyde's kind of special. And you also start to have issues with cross-reactivity because then it's going to kind of ask the question, okay, if we have a ketone, you can, I guess, rationalize why it would be making the aldehyde, but why wouldn't the aldehyde react with itself? So self-reaction can become a problem. So for now, just formaldehyde's what you'll see. It'll be good. Oh yeah, formaldehyde, secondary amine, ketone, or aldehyde. So this one could potentially also be, well, it wouldn't be benzaldehyde. But it could be an aldehyde like this. It's usually more of a ketone though, because formaldehyde itself is non-enolizable. So we can get successful cross reaction. Potentially another way that some people view these reactions, and sometimes it actually changes depending on the mechanism. You could imagine doing a crossed aldol between your methyl ketone and formaldehyde, and that would initially give you B as an intermediate. And you can imagine now the nitrogen doing an aza Michael addition because it's a soft nucleophile. So that would be another mechanism that's actually very reasonable. And so if I asked you to draw a mechanism of the Mannich reaction, there's actually a number of things you could draw that would technically be correct. Without going and doing a lot of different types of studies in a chemistry lab, it'd be pretty hard to do. Yeah, Michael addition is the same as 1,4 addition. The Michael addition is usually reserved for carbon nucleophiles, so it would be called an aza Michael if it's a nitrogen. Yeah, so Michael addition, 1,4 addition, and conjugate addition are all kind of interchanged in the literature. So sorry if I don't stick with one. pK of acetone, that's a good one. These are some reasonable problems. I think we've done probably extra commentary on most of these questions now. Good. Got any others? Let me check Piazza. Maybe someone wrote something. Never know. No. Oh, wait, there is. There is a question. On the direct alkylation of ester slide. Oh, I need to clarify that. Apparently I misspoke on a video. I will go inform later. It wasn't something to do now. Is this from the book? Okay, I will go see. I think I can get it pretty quickly. I won't be able to pull it directly onto my iPad because I always move it over from my computer and that takes a little while. 1930. Give me a moment. Oh, it's this one. I like this question. Let me go back to these notes. So we have ethyl crotonate. Actually, I'm going to leave that as a line to save me some time in a minute. We have ethyl oxalate. So this is one that is sort of, I guess, one step removed from examples we've had. And if you follow the arrows, you should be able to come up with the right answer, but it may take some pondering. We see we end up with this new product. So one thing to kind of start looking at is like, okay, here's a reaction that we don't completely know. We see sodium methoxide, and we see it's matched to the esters, so we know that transterification won't do anything. We can also go and try to see where do the two molecules fit on each other. So we can see we have the oxalate component. It appears there. And we can see we have this fragment now on the other side. So the bond we want to make somewhere is actually this one. Since carbonyls are electrophilic, that means that somewhere we're going to want to have this carbon become a nucleophile. So something that might not be obvious at first, but good to keep in mind, go back to my blue, is that the hydrogens right here are actually fairly acidic. And it's because we have this double bond next to the ketone. So let's use ethoxide to deprotonate this hydrogen. And at first it looks like a carbanion, but you can have resonance that pushes these electrons all the way over into the oxygen. So this is what people call an extended enolate, because you make the enolate through another pi system. Now we have what we need. We've made this carbon nucleophilic. So this carbon actually, this enolate has two nucleophilic carbons. It could be the normal alpha position, or it could be one more over. The one more over ends up being more reactive because it's a bit more accessible. And it also ends up giving you the right product. And now we can have this react with diethyl oxalate. Oxalate esters are actually even more reactive than your normal ester because it's kind of like having an electron withdrawing group right next to the ester that increases its electrophilicity. And from here we can see that we go to our tetrahedral intermediate. And if we make a tetrahedral intermediate, oops, one too many bonds. We regenerate this ethyl ester, and now we are almost to the product. We just need to collapse this tetrahedral intermediate, and it goes. This ends up being selective because the product ends up being less reactive as the starting material. So the reason 1,4 addition doesn't happen is one, the Well, that's a good question. Um, I think that probably the information you don't know is that this molecule is a really good electrophile. Actually, much better of an electrophile than the um, the initial double bond of the ester. But that's a very good question because we are choosing to have a 1,2 addition over the conjugate addition or the 1,4 addition. So these tend to not self-react as much. And I would say that you would not have enough information on, say, like an exam. And this is probably already one step past what I would put on an exam right now. But given the product and seeing how they're connected, you can come up with a reaction. So the question was how, since this equilibrium in solution, if we want to draw it a bit more specifically, will actually be mostly in favor of the neutral form. That means when we make this extended enolate, we also have more of this alpha beta unsaturated ester around. And so the question is, why does it not add to this 4 position? And instead, why does it add 1, 2 to the oxalate? So based off of the information that I've given you in class, you would expect this reaction to take place because resonance stabilized enolates are soft. This is because they're using this weird electrophile that is very reactive, and it kind of overtakes everything else. So from the perspective of mechanism and trying to rationalize how things can come together with reasonable bond formations, I think this is good for a practice problem to get your mind thinking the right way, especially maybe a little bit outside exactly what we've learned. I probably wouldn't put this on an exam. And trying to guess the product would be very difficult without giving more information. I was confused where you started the number. Oh yeah, so for talking about 1, 2, and 1, 4 additions, this is consistently how you would number things. For determining cyclizations, those numberings are a bit more free form. Cool. If there aren't any more questions, I'll probably let you guys go. I'll be back here same time, same place tomorrow night. Ready for some more questions if you have them. Have a good evening. I will get the template uploaded later tonight. We should get all the feedback from the TAs. All right, have a good one.